All right. Hello, everybody. Welcome to Colloquium. Hello, people of the internet. It is my great pleasure to introduce Jorge Moreno. Jorge is a professor at Pomona College, which is my alma mater, but don't blame them for that. I was already gone by the time they got there. Jorge is going to be talking today about a paper they wrote that was recently published in Nature Astronomy, which one very prominent theorist said solved one of the biggest problems in theoretical studies of galaxies at this present moment. So I'm very excited to hear them talk about that. They did this all while being a professor at a primarily undergraduate serving institution. So super person, and also while trying to decolonize astronomy. I'm really excited to hear all about how dark matter is solved. Take it away, Jorge.
Thank you for the nice intro. It's a pleasure to be back. I came here for the first time in 2001, and then I came back in, oh, what happened there? Oh, there it is. It's back. Yeah. Sorry about the technical difficulties. Excellent. Almost there. All right, thank you. Sorry for the technical difficulties. There it is. So it's a pleasure to be here. I came in 2001 and I came back in 2017. So it's great to be back again and talk about something entirely different. Over the last few years, I've been focused on mergers of galaxies, and this is my first paper looking at low mass galaxies. And I think it's a really nice paper. And the thing about low mass galaxies, especially when they're satellites, is that their history can be really strange. So usually when you're a tiny galaxy in a massive system, usually you have two options. Either you assimilate with the massive galaxy, you merge with it, or you get completely disrupted. So that's usually the two options. Today I will talk about galaxies without dark matter, and it turns out that they choose a third path. But before that, I want to acknowledge that I conducted my work on Tonga, Gabrielino land, indigenous land. I have indigenous roots myself. From my family is from the border between the US and Mexico. So it's really important for me to make this acknowledgement. I also like to acknowledge the people who clean our offices, who grow our food, people who maybe didn't have the access or privilege to do science as we do, but they're just as curious as the universe. So whatever we do, whatever discoveries we make, it's important to honor them because we're doing it for them in a way, right? Of course, I like to acknowledge my co-authors. This is my first time writing a Nature paper, and the referee process is brutal. So I'm so glad that this is finally out. And here's an outline of what I'll talk about. So first, I'll give some background. And this is especially for people who maybe haven't been working on simulations of galaxies, or maybe the students who just got here a few months ago. This part is for you, but also for experts. Maybe you can see other ways of explaining things that you've known for many years. Then I'll talk about galaxies lacking dark matter. They were discovered 3 years ago, and we were able to make them in simulations. Then I'll talk about this really fancy simulation called Firebox. So Firebox uses fire. Fire stands for feedback in realistic environments. And we have been able to reproduce many properties of galaxies across many scales, but this is the first time we actually use that model in a cosmological box. Then I'll talk about the challenges faced by other simulations and explain why, even though there's been like 15 papers, people trying to make these galaxy simulations, I'll explain why I think they haven't been able to do so and why Firebox is so novel. And then of course, at the end, I will talk about the physical mechanisms making these dark matter deficient galaxies and make some predictions so observers can go out there and find the things we predict. So let us start with background. So it's been known for the last at least 50 years that galaxies have dark matter. For example, this is a video of Andromeda, and basically for you to be able to see how quickly Andromeda is spinning, you will have to wait millions or billions of years. But if you measure spectra, if you measure absorption lines or emission lines, you can see that this is rotating. And not only can you infer the direction of motion, but you can actually quantify how fast the galaxy is spinning as a function of distance from the axis of rotation. And you can infer something like a rotation curve. And the thing is, if you apply just classical mechanics, if you measure the circular velocity, you can then infer the dynamical mass. And the dynamical mass is the mass of everything, not just the stars, but everything that is in the galaxy. So Vera Rubin used this for things like the Milky Way or other galaxies. And this dotted line is what you would expect just from baryons. But when you make observations, you see that there is a huge discrepancy. And you need to invoke something else, this mysterious dark matter, to explain why things are moving so quickly. It's kind of like if you were looking at your laundry and it was spinning around and you didn't see the laundry machine, you ask yourself, what is containing all that stuff, right? It's probably dark matter, right? Now this is for rotation-supported galaxies, but then you have galaxies like this giant elliptical or this tiny spheroidal. And for this, these are dispersion-supported systems. So you need to use a different method to infer the dynamical mass. So for our rotation-supported system, we saw that you can use the rotation curves. For dispersion-supported systems, you use the line-of-sight velocity dispersion. So you look at your stars, you measure their line-of-sight velocities, and you make a distribution, and then you can fit a Gaussian, and the width of that Gaussian is a velocity dispersion. And from that, you can infer the dynamical mass. Now, people have been doing this, and something we find is when you look at galaxies and you go down to low mass galaxies, so you start with something like the Milky Way and you go down to tiny galaxies, if you measure the dynamical mass, it doesn't shrink as quickly as the stellar mass. Another way to think about this is once you go into the low mass regime, galaxies tend to be more and more dark matter dominated. So how do we explain this? There are two ways you can do this. The first one is with something called abundance matching. So if you heard that term before, cool. If you haven't, then I'll give you a mini lecture about abundance matching. And it works like this. So here I'm showing you the stellar mass function. I'm showing you the number of galaxies per unit volume in beams of stellar mass. So on this side, you have massive galaxies. You don't have many of them. And once you go to low mass galaxies, you start having lots and lots of them. So this is what you get from the real universe when you measure and count galaxies. But from simulations, you get this solid line, which is the halo mass function, the number of halos per unit volume in any given halo mass. Now, the solid line is the halo mass function. And if you multiply that by the fraction of mass in baryons, you can think of this as if you were to share all the baryons in the universe into halos, that's what the baryonic halo mass function would look like. Another way to think about this is if you didn't have any feedback, if you were able to transform all the baryons into stars, that dashed line would be the stellar mass function. The reason there is a discrepancy is because you have feedback. On the massive end, you have AGN feedback, which is stopping gas from transforming into stars, and the other way around. And in the low mass end, you have a stellar feedback from star formation, which also prevents baryons from gas from transforming into stars. What does this have to do with the question I posed before? Why are low mass galaxies more dark matter dominated? So with abundance matching, what you do is you look at abundance. So if I draw a line like this line is telling you that if you're on that line, there is one object per 10 to the 5 megaparsec cube on average. So you can say, oh, at that number density, at that abundance, you will have one 10 to the 12 solar mass galaxy. And also you will have a 3 times 10 to the 14 dark matter halo. So you're kind of looking at how infrequent they are as a function of density. It's kind of like if you're looking at upper middle class people and you go to the rich and then you go to the ultra wealthy, to find an ultra wealthy person, you have to look at a bigger volume because they're rarer, right? So what we do is in the observations, we look at rare galaxies. In the simulations, we look at rare halos and then we match them. So I can match these two. I can do it at other masses and I can do it at a bunch of times. And something that you notice is when you look at the massive regime, the discrepancy between halo mass and stellar mass is really big. Then when you go to the knee of the mass function around the scale of the Milky Way, it shrinks, and then it gets bigger and bigger again. We were talking about low mass galaxies. When you go into the low mass regime, the discrepancy gets bigger. And this is from abundance matching. So with this mapping, you can do a one-to-one map between stellar mass on the y-axis and halo mass on the x-axis. And this is not just a linear relation, but it has a bend. So this bend tells you that that discrepancy grows when you are looking at galaxies more massive than the Milky Way, but also it grows for tiny galaxies. So for example, at this scale, the mass ratio would be 200 to 1. But if you go to lower mass galaxies, it goes to 2,000 to 1 or 20,000 to 1. And I want you to remember this. The expectation from lambda CDM is if you're looking at tiny galaxies, low mass galaxies, they are supposed to have a higher fraction in dark matter. They tend to be more dark matter dominated. I want you to remember that. And observationally, you can measure the dynamical mass by measuring the motions of stars, and you find that, yes, indeed. Here I'm showing you a paper from Toller 2011, and this is the light to mass ratio. So you measure how much mass you have within the effective radius and how much light, and you take the ratio. And you find that when you're looking at low mass galaxies, that ratio tends to increase. If you're looking at the effective radius and you go into the low mass regime, you will be more dark matter dominated. I need to remember that. So at each chunk of my talk, I will give a mini review because I know sometimes we kind of lose track of things. And this is an opportunity for questions. So just a quick mini review. We can use rotation curves to infer the dynamical masses of rotation supported systems. We can use the line of sight velocity dispersion to do this for dispersion supported systems like elliptical galaxies. And when you look at low mass galaxies, when you go into the tiny galaxy regime, galaxies tend to be more dark matter dominated. Any questions? So is there a physical reason? So when you're looking at tiny halos have a harder time at retaining their baryons. So if you have, you're able to retain some gas. If there is reionization, if there is like a supernova going off in the galaxy next door, or if you make a supernova here, it will blow out the gas and it will basically evacuate the halo. So it's not that efficient. So when you're looking at the tiniest systems, you can have let's say a supernova explosion, it blows out the gas, but because there is so little mass to begin with, that won't pull the dark matter. But once you go from the tiniest halos to the ones in which we call the classical regime, which would be around like the LMC or below. In that regime, it's not just one supernova. You can have a burst of star formation, and then you can have those outflows, but you're putting enough mass out, you're evacuating enough mass that the dark matter can follow. So if you follow, for example, the dark matter profile, it actually goes from a cusp to a core. But there is like this sweet spot that if it's too massive or if it's not massive enough, you won't be able to see that. Does that make sense? I like to make the analogy with coffee. Yeah. Imagine you have an espresso cup and you have an Americano cup, and you put them in your microwave and you crank up the heat. Which one is going to make a mess first? The Americano? No, the espresso, right? Because it has a tiny potential, whereas the Americano can hold things together. And that explains why that mass ratio increases so much, I think. All right, so any questions from folks on Zoom? Are there any questions in the chat? All right, so if you don't have any questions, let's hold them for later. So let's talk about galaxies lacking dark matter. So these were discovered in 2008 by Peter Van Dokkum, who is Erica's former PhD supervisor, and Shani Danieli, who's one of my best friends. And these galaxies, here I'm zooming into the group NGC 1052. And that's NGC 1052 is that massive galaxy there. And here you can see that blur, that's the NGC 1052, which is a satellite of that massive galaxy. and it seems to have no dark matter. And that caused a lot of controversy because, well, we expect low mass galaxies to have a lot of dark matter. I told you to remember that. So people went and, for example, observers were like, oh, they have to be wrong. So they went and remeasured this thing with, especially the group in Tenerife, they did this and they found that, oh, actually, we don't think we agree with Shani and Peter van Dokkum. So then Shani got Hubble time and rechecked, and yes, it's still dark matter deficient. People using simulations, they couldn't find them in cosmological simulations. And then people who don't really like the idea of dark matter, like the modified gravity groups, they were like, you know what, it's time to get rid of dark matter. Maybe we need to, maybe Mond is right. So this is a picture of Shani and Peter with the Dragonfly instrument, which is really cool. And they found this galaxy. I'm told that they just found it by chance because it looked like this, and it had this weird globular cluster population. So what they did is once they found it with Dragonfly, they got time on Keck and time on Hubble, and they were able to find line of sight velocities for the galaxies in the group and the globular clusters in this galaxy. So on this side, you have NGC 1052, which is the central galaxy. You have the other satellites, and here you have DF2 and the globular clusters. They measure, by measuring the stellar light, you can fit a search profile. They infer that the stellar mass is around 10 to the 8. But so the expectation from abundance matching, for example, the expectation is if you have a 10 to the 8 galaxy, the line of sight velocity dispersion should be around 30 to 40 kilometers per second. So that is the expectation. What they measured is actually only 8 kilometers per second. So now we can use this gymnastics here. We know that if you measure the line of sight velocity, you can infer the dynamical mass. You can do some algebra. This is your dynamical mass. And then they found that the dynamical mass matched the stellar mass. Another way to put this is that there is no room for dark matter, which is really intriguing, right? The next year, they found another one. So this is DF4. So from now on, I won't tell you the whole telephone number. I'm just going to call them DF2 and DF4. So there are two galaxies in the real universe that seem to have no dark matter, which puts the whole lambda cold dark matter model in a bit of a crisis. And this is a picture of the group, the NGC 1052 group. This is the central galaxy. Here's DF4, and here's DF2. So these things are satellites of a bigger group. So the question we might ask is the standard lambda CDM model in trouble? Or is there something we can do with simulations? Now, Shani and I have been friends for a few years now, and I strongly encourage all of you to work with your friends. But I was working with massive galaxies, so I never saw myself working with tiny galaxies, but now we have a paper together. And Shani, if you haven't invited her yet, invite her. She's really awesome. So let me tell you about the simulations we use to explain these galaxies. So this is called Firebox. Fire stands for feedback in realistic environments. And box basically tells you that we're using a big chunk of the universe. And here's a video of Firebox. So there's been a lot of cosmological simulations out there. If you're older like me, you might remember like 10, 15 years ago, we had the Millennium simulation. And then around like maybe 10 years ago or less, we had the Illustrious and Eagle, the simulations with hydrodynamics. I would say that the jump between Millennium and Illustrious is as big as between Illustrious and Firebox. The thing with Firebox is not just about simulating hydrodynamics, but also resolving the multi-phase turbulent structure of the interstellar medium, which we have been doing with SUM simulations, and this is the first time we implement that in a cosmological setting. So we're able to resolve giant molecular clouds in a really big box. So let's quantify this in a couple of ways. So when you create a cosmological simulation, there are two things you want to maximize. You want to optimize resolution, and you want to make it as big as you can. So if you increase the resolution, you're able to resolve the structure of galaxies at really high detail. And if you have a really big box, you can have a huge diversity of environments. You can have galaxies that grow up in a cluster or in groups or in a field. Just like people grow up in maybe tiny towns or small towns or cities or huge megalopolis. The same is true with galaxies. So you want to capture that diversity in environments by having this box to be big enough. Now, if we compare with zoom simulations of single galaxies, this is where we are. So for example, you can see there like the old fire runs, or you can see latte, which basically they focus on a single system. And we see that our resolution is comparable with the zooms. Now, if we look at cosmological simulations like illustrious and this is where we are. So if you follow those dashed lines, we like to call that discovery space. The higher you go along those dashed lines, you can discover new things. And we're comparable, for example, with illustrious. The green squares are illustrious 300, 150. So we are comparable with them. Something I should mention is that there are two types of symbols here. Some of them are filled symbols and some of them are empty. The filled symbols like firebox, we resolve the multi-phase structure of the ISM. The ones that are not filled like TNG, they don't. What they do is, if you want to say, for example, get a rule for star formation, they take the Kennicott law and they just tweak the parameters to match that. Whereas when you are able to resolve the ISM like we do in fire, you are able to, the Kennicott law becomes a prediction of the model. It's no longer an ingredient that you have to tune to, but rather that's something that emerges naturally from the model, which makes its prediction power much better than things like TNG or Eagle. Now, this is one way to characterize cosmological simulations. Another way is to look at the dynamical range. So the dynamical range is, this is the spatial resolution versus the box size. So that's where firebox is. If you look at the zooms, what happened here? Oh, it's back. Sorry about that. So if you compare with the zooms, this is. That's okay. So I need to share my screen, right? Sorry about that, folks on Zoom. Is that on Zoom now? All right. So another way to characterize the power of cosmology.
On your keyboard, I'm sorry. There's a little square out of the brush area. Is it fine now? Is it okay here? No. That's the presenter view. Yeah.
Sorry about that, folks.
Yeah. That should be better.
Thank you. Is that good? Awesome. Thank you, Andre. So I was saying, to characterize the power of cosmological simulations, one way is to optimize resolution and volume. Another one is to compare the spatial resolution with the box size. And in this case, we see that we're actually higher on the zooms. And when you compare to cosmological simulations, we're actually doing better than Eagle and even TNG 50. So there is a lot of potential here. Just to illustrate, this is a chunk of the cosmic web. You can zoom in and zoom in a little bit more and even more, and you're able to characterize the properties of giant molecular clouds in a cosmological context. This is the power of this dynamical range. So this is the next generation of cosmological simulation, and I expect a lot of cool discoveries in the next few years. And just to be a little bit fancy about this and brag a little bit more, this is one of our galaxies. This is a simulated galaxy, and we're able to capture the detail and the physics at really high resolution. So what do we find? So I'm focusing on low mass galaxies. So here I'm showing you the mass in dark matter versus the stellar mass. And the observations are only able to look at the half mass radius, the effective radius. So that's what we're reporting here. And the color coding is a fraction of mass in dark matter. So if you're kind of a pinkish, it means you're dark matter dominated. If you are greenish, you're dark matter deficient. Now I'm only showing you centrals. And just to guide the eye, I'm putting some 1-to-1, 10-to-1 lines. And you see that These galaxies are following a trend, are following this band, and the slope of that band is below unity, which explains that when you go to mass galaxies, they tend to be more dark matter dominated. This regime here would be the dark matter deficient regime, and above that, it would be the dark matter dominated regime. And this is where DF2 and DF4 lie. So you see that none of my galaxies are down here, but I'm only showing you central galaxies. I'm not showing you satellites. Now, we know that if you have a galaxy and you have a central galaxy, if you have a halo and it has a central galaxy, it tends to have satellites. And in some cases, you can have, and those satellites have subhalos. And in some cases, you can have satellites with their own satellites, like the LNC and the SMC, which means that you will have a subhalo and a sub-subhalo. So we call those substructures. So when I include substructures in this plot, you see that things change. You see that in general, the triangles tend to be below the relation because to go down, you need to lose dark matter. To go to the left, you need to lose stars. And when you become a satellite, you're losing stars and gas. So in general, galaxies tend to go down and to the left. But if we look at these 7 galaxies here, those are in that regime, that dark matter deficient regime. We're able to find 7 galaxies in a simulation dominated by dark matter, and these galaxies are deficient in dark matter. If you look closely, right next to there is another triangle that we didn't put a symbol around. That's actually a double nucleus. So you have a merger of 2 galaxies with 2 nuclei, and that would be the secondary nuclei. So we decided to not include that in our samples. Now we found 7, and we were thinking of names. Some people thought about the Disney characters, but I didn't feel it was appropriate, especially for small people. That's not something I don't want to exclude them. And I've been telling the community we should move away from the term dwarf galaxy and maybe use tiny galaxy or low mass galaxy. It might sound trivial to us, but we don't experience that experience, right? Also thought about the 7 sisters, but I'm not a woman, and I felt it was not my place to appropriate that name. A friend of mine is a Cherokee physicist. His name is Doug Ingram. And a few years ago, he told me about the 7 Cherokee clans. And they have really cool names. So I asked Doug, can you talk to the elders and ask permission so I can use their names? And they said yes. So we named the 7 galaxies in honor of the 7 Cherokee clans. So each of these galaxies has a personality. So let me tell you a little bit about each. So this is Wolf. And you can see that tiny galaxy there. And this is the dark matter mass. So this is what you would see with the Hubble Space Telescope. This is the dark matter distribution. And you see that there isn't a subhalo associated with Wolf. And here's Wild Potato, same situation. And here's Paint is a little bit fluffier, but it's the same thing. So a question to you, people in the audience, is what do these 3 galaxies have in common? So they seem to have like tidal tails, right? So maybe interactions have something to do with it. Anything else? They're really close to a massive galaxy. Yes. Anything else? They don't seem that blue. They look reddish. They have all stellar populations. Anything else? Are they the only ones being affected? If you look at the central galaxy, it looks a little bit disturbed, right? Like, for example, this one here looks like the Sauron eye from Lord of the Rings. And I think the culprit is because this tiny galaxy just crossed it and disturbed it. So those are some of the things they have in common. This is long hair. Long hair is actually really far away from the central. It actually went through the central. It crossed around like maybe 6 kpc. And right now it's around 400 kpc. It crossed in a very radial orbit. It left the halo, it became a central, and now it's on its way back. And this is the dark matter distribution. And the last 3, they're actually members of the same group. Deer, Blue, and Bird, they are cohabiting this group. And actually, Blue and Bird, they came together and they have interacting with each other, kind of like the LMC and the SMC. And this is the dark matter distribution. Really neat, no? So if we look at this plot again, then you can see where these galaxies lie. And I want to bring attention to a couple of things. The first thing is that all galaxies are at least 10 to the 8. So they're between 10 to the 8 and 10 to the 9. we notice that paint is the most extreme one. Its dark matter fraction is below 1%. And just a quick mini review. There are 2 dark matter deficient galaxies in the real universe so far observed. 7 dark matter deficient galaxies in Firebox. They tend to be satellites. They tend to have tidal features. They tend to have red stellar populations. 3 of them are very close to their massive host. 1 of them is really far away, and at some point it became its own central. And 3 are in the same group. And Wolf is the one that resembles DF2 and DF4 most. And this was really hard to make. I was celebrating when I actually compared the 2. They are really similar in many things. The mass, the velocity dispersion, the morphology, the self-stitch index, the ages, we do a really good job. Which now allow me to talk about the limitations in other simulations. Even though there's been like 10, 15 papers trying to find these things in simulations, let's talk about why I think you don't find them. I will talk about 3 simulations in particular. I'll talk about New Horizon, Eagle High Resolution, and TNG50. And these are the papers that I will discuss. So let's start with New Horizon. So I found these galaxies in the day before Christmas 2020. I sent Shani some pictures via WhatsApp. And then in April, Jackson published a paper and I panicked. I'm like, oh, they scooped us, but they didn't. And if you go to figure 1 of Jackson, they plot the following. On the y-axis, you have the stellar mass, and on the x-axis, you have the ratio of dark matter to stellar mass. And here I'm showing you the Firebox centrals. So this side would be dark matter deficient, this other side would be dark matter dominated, and this is where the observations lie. I'm only showing you centrals. When you include satellites, then you have the systems, and you see that our galaxies are on the dark matter deficient side. Now this plot is slightly different from the first one I showed you, because before I was just showing you the mass within R50, within the effective radius, because that's what they measure in the observations. Here I'm showing you the entire mass in the subhalo. Now, so how did Jackson do? So these blue dots are Jackson. And they say basically, oh, we're going to define dark matter deficient galaxies to be below 10, which doesn't make much sense to me. So basically, if 90% of your mass is dark matter, you call that dark matter deficient. And I think that you're kind of pushing that. It is true that they are below the main relation, but they are not quite in the dark matter deficient regime. And why would that be? So if you look at their paper, they show a histogram of this minimum distance from the host in units of the virial radius of the halo. So if you're right at the edge, that would be unity. If you're halfway in, that would be 0.5 and so forth. And they find that their satellites only go as far as 20% of the virial radius. They don't go deeper than that. And we're going to see that that's not the case for our galaxies. Let's talk now about the Eagle simulation. So this paper by Ying, they looked at Eagle and Eagle high res. Now with the Eagle simulation, they only look at galaxies between 10 to the 9 and 10 to the 10. DF2 and DF4 are around 10 to the 8. So these are not good candidates at all. They don't have the resolution to look at things like DF2 and DF4. If you look at Eagle high res, they actually go down to 10 to the 8. And actually this dot here is quite intriguing because it's below that 50% line. But just by looking at their paper, it's not clear if that mass is around 10 to the 8 or closer to 10 to the 10. So by just reading the paper, it's not clear if that's a good candidate for DF2 or DF4. So I sent an email to Ying, say, hey, can you give me your data so I can put it in my paper? And he kindly agreed, and this is where that data point is. So with Eagle high res, you're actually able to go into the dark matter deficient regime, but it's still too massive compared to DF2 and DF4. And if you measure the line of sight velocity dispersion, it's also like 2 sigma above what you find in the observations. So even though it's a reasonable candidate, it's not quite able to mimic DF2 or DF4. Getting the velocity dispersion right has been a huge challenge for simulations. So this is looking at DF2 again. The velocity dispersion is around 8 kilometers per second. And now this is with Eagle, no, this is with Illustrious TNG50. This is a paper by Laura Sales. And here I'm showing you the line of sight velocity dispersion as a function of stellar mass. The color points are the symbols with error bars are observations, and the rest is simulations. And they find that none of the TNG50 galaxies are able to get velocity dispersions as low as the F2 and the F4. But when you look at Firebox, when you look at Wolf, you see that our velocity dispersions are tiny. Now, this depends on the line of sight of the direction. So what we do is we take X, Y, Z using the box coordinate system, and we find that in the Y direction, you actually go below the F2. So this has been a huge challenge. Now, remember at the beginning of the talk, I was saying to estimate the dynamical mass in dispersion supported systems, you need to know the line of sight velocity dispersion, but you also need to know the size of the galaxy. So with Firebox, we look at satellites between 10 to the 8 and 10 to the 9. Here's the line of sight velocity dispersion versus the stellar the size. I can put a few lines here that indicate the dynamical mass. So this is the formula we use to estimate dynamical mass. This is where the F2 and the F4 are. And here's where our sample of 7 is. And you notice that Wolf is compatible with the F2 and the F4. Getting a galaxy in a cosmological simulation with the size and the velocity dispersion consistent with the observations has been really hard. And so we're really happy that we did this. So just to give you a mini review, cosmological simulations have struggled to produce this kind of galaxies. They've been unable to make dark matter deficient galaxies in general, specifically those with low enough line of sight velocity dispersions. And we find that Wolf is the one that resembles the F2 and the F4 the most. And I think, in my opinion, this is a huge accomplishment. Any questions?
Previous ones that didn't get these. You said it was more of resolution for its box, the simulation size, but are there differences in stellar feedback and stellar information that could also account for it?
So the question is, so how are our simulations different from the ones that weren't able to produce these galaxies? One of them is being able to resolve the physics of the ISM more or less well and feedback too. But there's another reason. Something I found is that when you have a cosmological simulation, you have an automated algorithm that finds galaxies. So I applied that algorithm and it didn't find these 7 galaxies. It failed to find them. And so I think it could be the case that some of the simulations, like the one by Jackson, those galaxies might be there, but they didn't find them. And now I was on sabbatical, so I was looking at system by system and checking by eye, and I found them visually, but the algorithm didn't find them. And I like to make the analogy, for example, now that you have graduate students visiting, imagine that you say, you know what, I'm only going to look at GPA, or I'm only going to look at GRE scores. Chances are you're going to find good students, but there are going to be some students that you won't find because you're just in an automated method. It's better to use a more holistic method to find good students. As far as cosmological simulations, we need to think harder about these algorithms.
Following up on that, is there a way, are you thinking of a way to change the algorithm in the future? So maybe kind of things that we need to go by?
I would hope so, because if you have a bigger box, it's going to be harder to use the eyes, use your eyes. But I think that's for someone else. Like, I'm not an expert on these algorithms, and I just pose a challenge for people who do that kind of work. No. Yes. So yes, getting something from like Wolf is really great. And we make predictions that there should be, we make a prediction that if you look at massive galaxies with at least 10 to the 11 solar masses, a third of them should have at least one satellite that is dark matter deficient. So that is a prediction we make.
So you have a
So with globular clusters, they tend to be smaller. So the thing with DF2 and DF4 is that they are bigger than a kiloparsec. That's what makes them different. And in fact, these low mass galaxies do have their own globular clusters. And I guess the formation is, these used to be massive galaxies with a lot of gas and dark matter that was just stripped away. Was there another question?
So you said that there's resolution deficiency in some of these results, especially with other papers, and that means that they can't produce those dark-matter-deficient satellites. Would you expect that the general, like kind of like 1/3 of satellites, be 1/3 galaxy satellites are dark-matter-deficient? Would that practice stay constant if you were to increase resolution further, or would you expect to see that ratio change?
So the question is, if we were to use a simulation with higher resolution, would that number, that 30%, stay the same? I would say yes, because I don't think this is driven by resolution. If we look at Wolf, which is the tiniest one, at redshift 0 has 3,000 particles, and it started with 50 times that. So you have a whole population of galaxies that are well resolved, they have a healthy budget of dark matter. And I'll talk a little more about why I don't expect high resolution galaxies which are less massive to be like this. So I'll go back to that. Was there another question? So let's talk about how these galaxies are created. And I kind of gave away a little bit of how this happens, but let me talk about this a little bit more. I think this picture gives a few clues. There has to be a massive galaxy, and maybe there are interactions because you see these tidal tails. So something I can do is I can plot the stellar mass of the central versus the stellar mass of the satellite. Let's paint some lines just to guide the eye. So for example, if you were looking at one-to-one mergers, you would be on this dash solid line, dash black line. DF2 and DF4 are here. So in GC 1052, that massive elliptical is on that line. And our 7 galaxies are here. And we find that 30% of hosts above this line should have at least one dark matter deficient galaxy. So if you want to look for dark matter deficient galaxies, look at galaxies with at least 10 to the 11 solar masses, and look at satellites that have at least 10 to 8 solar masses. And you will find that about 1/3 of them are dark matter deficient. Another thing to notice is that the symbols are going along a diagonal. So it seems like the mass fraction has to be 1,000 to 1. Notice that it has to be at least 10 to the 11 galaxies. If you start going down to, say, the Milky Way scale, we predict that Milky Way galaxies won't have satellites like this. We haven't found any in the local group. If we look at Milky Ways outside the local group and find them, that would be a direct challenge to our predictions. We predict that Milky Way shouldn't be able to have these kinds of satellites. So just to summarize that, mass ratio should be around 1 to 1,000. And we predict that 30% of centrals with at least 10 to 11 solar masses should have at least one dark matter deficient galaxy. Now, this is the stellar mass ratio, but we also can look at the interaction history. So here, this is Wolf. I'm looking at the distance between the satellite and the central as a function of time from the moment it became a satellite to today. So you see these oscillations because this galaxy is doing this. The vertical lines are pericentric passages. The red vertical line is the time when of closest approach. The solid gray line is the radius of the halo, of the host halo. And the dotted line is 5%, is 10% of, no, it's 5% of that. Now we can look at the evolution of mass. So this is the total mass of the satellite. This is what the dark matter is doing. This is what the stars are doing, and this is the gas. So you notice that around like 11 gigayears after the Big Bang or so, even though you're losing dark matter and you're losing stellar mass, the dark matter content plummets, whereas the stellar mass content is diminishing slowly, and it becomes dark matter deficient at that point. And if we compare this with the orbits, we notice that that happens when you go within 5% of the virial radius of the host. It's not just any interaction. It has to be an interaction such that if you have your central galaxy and you have your dark matter halo, it has to go within 5% of the radius for this to be effective, which is basically the tiny galaxy is crossing the baryonic body of the central galaxy. And when it does that, in extremely radial orbits, that's when it becomes dark matter deficient. You need extremely deficient, you need extreme orbits to be able to accomplish this. So to summarize, this is what we can do. On the y-axis, I had the minimum distance between the satellite and the central in units of the virial radius of the host. And on the x-axis, I have the stellar mass ratio between the satellite and the central. And these lines indicate DF2 and DF4. We only have information about the stellar mass ratio. We don't know what they did back in their history. That's something we cannot infer directly from observations, but at least we know their stellar mass ratio. Our 7 dark matter deficient galaxies are here, and they occupy a really unique region of parameter space. You have to go within 5% of the virial radius of the host, and the stellar mass ratio has to be around 1 to 1,000. If you meet those two conditions, you will become a dark matter deficient galaxy. If you are on this side, chances are you just merge very quickly. And if you're on this side, chances are you get completely disrupted by the host and you just build up the stellar halo. But if you're in this critical regime of 1 to 1,000, you can survive. But you have to be in extremely radial orbits where you actually pierce through the baryonic body of the central galaxy. And it's not like, in general, satellites just do this 2 or 3 times and then they dissolve. Some of these, for example, blue passes 10 times. It crosses the central galaxy 10 times and it's still around. And BIRD does this 14 times. So these are very resilient galaxies. Just to give you a quick review. In 2018 and 2019, Peter Van Dolkom, Shani Danieli, and others, they found 2 dark matter deficient galaxies in the NGC 1052 group. This motivated us to use Firebox and find them in simulations, and we found 7 of them. And to create a dark matter deficient galaxy, you need 2 conditions. You need the stellar mass ratio to be around 1 to 1,000, and the satellite has to pierce within 5% of the radius of the host halo. And we predict that 30% of centrals with at least 10 to 11 solar masses should have a satellite that is dark matter deficient. And that these things, they plunge to the central galaxy multiple times. Now, as a person of indigenous ancestry, I feel very connected to these galaxies. These galaxies have 2 options. Either you assimilate to the dominant culture or you get destroyed. These galaxies chose a 3rd path. They decided to confront the Goliath multiple times. They paid a price. They lost their dark matter, but they are still here. So I think of myself, I'm someone with indigenous ancestry, but I don't speak an indigenous language. I have a European name. I speak European languages. I wear European clothes. I was assigned a European gender, but I'm still here and I'm thriving. So huge respect for these galaxies. Thank you. Are there any questions?
So I guess I still ask the question wrong. It appears that when these small galaxies plunge into the dark matter, and their gas is also circulating. So I understand the gas the pressure goes but I'm not sure I understand then what is differentiating the stars from the dark matter. Both of those can be treated as, n-body kind of calculation. So what's still the physics behind stripping out the dark matter and leaving the stars?
So the question is, why are the stars resilient and the dark matter not? And as you said, with the gas, well, you have ramp pressure stripping in addition to tidal stripping, so that's explained. But the thing is, when you make stars, you make them from cold dense gas, which is strongly gravitationally bound to that satellite. So the stars are born there intend to be strongly gravitationally bound. So they have really bound orbits, whereas the dark matter, they have these elongated, loosely bound orbits, so it's easier to strip. That's what we suspect But we need to go back to the simulations, and we're planning to do high resolution zooms and actually quantify that.
Okay, I'm taking artistic liberty here. So the maybe I should ask the Mond people this instead of you, because I don't think you're a Mond person. But why were the Mond people so excited about that? Because the prediction from Lambda CDM, right, is that there's a power law between the like in the mass distribution. It's like feedback isn't necessarily a prediction of Lambda CDM, and this is really an issue. If anything, yeah, if anything, this would go the other direction. It seems like to me that there's dark matter deficient galaxies. If you see what I mean.
So I don't know. I guess it's like LCDM is not. You don't expect low mass galaxies to not have dark matter. So hey, that's a problem with that model. But the reality is we need to understand feedback. We need to understand variance, and that's what we do with FIRE. Now, I'm not saying that we don't need to worry about MON anymore. We're just mitigating the exigency for those models. With a lambda CDM dominated universe, you can create galaxies like this.
So following on from the first question about why does it strip the dark matter and leave the stars? I may not know very much about clusters in general, but these diffuse galaxies seem like, if anything, they would be a lot more susceptible to their stars getting stripped and disrupted and sent every which way, just based on the way that clusters, especially open clusters, tend to be pulled apart really easily. So in a similar vein, why are the stars not stripped and scattered to the winds?
So what I'm saying is that stars are stripped, but dark matter is stripped more efficiently. But you are losing stellar mass, and you go from something of around 10 to the 10 solar masses down to 10 to the 8. So there is a stellar mass loss, but it's not as dramatic as the dark matter mass loss. Yes. So maybe I can show you this plot here. So this is a fraction of retained stellar mass on the x-axis and fraction of dark matter mass, retained dark matter mass on the y-axis. So how much dark matter mass you have now versus when you first became a satellite, and the same for stars. You do see that you lose stellar mass, but you lose more dark matter mass when you become a dark matter deficient galaxy.
Thanks. Yes, I was wondering what happens to the dark matter that gets stripped? Like, is it on really tightly bound orbits, or the orbits of this dark matter? Do they loop back to the apocenter of the satellite orbit? It's kind of where does the dark matter end up?
The question is, where does the dark matter go? I don't know. That's an excellent question.
Can I have a part B?
Yes.
Are there any of the centrals, maybe they are actually, they're disky, right? They're not just elliptical blobs. So it'd be interesting to know, do they settle in a plane? Or?
Yeah, there is so much good stuff to do.
Thank you.
Awesome. Let's thank Jorge again for an excellent talk.
And were there any